In Chapter 16, we're going to look a little more in depth at some acid-base chemistry. We looked at it last semester at a fairly surface level, but now that we've established some information about equilibrium, we can look at it a little more deeply, and so that's what we're going to do in this chapter. Our starting point is kind of an odd one. We're going to start with looking at water itself. Since most of the acid-base chemistry that we're going to talk about here is going to be an aqueous solution, we have to understand what's happening in that water solution. And so the first thing to know is that water itself is always in an equilibrium and undergoing what we call autoionization, which would be the self-ionization of water. So essentially what you have is you have two water molecules that interact with each other, which is happening all the time in water, and they are in equilibrium with hydronium ion and hydroxide ion. And so you have this equilibrium reaction happening all the time in any beaker of water that you ever have. You have some water that turns into the hydronium ion and the hydroxide ion. And so we know that those two substances are the substances that essentially affect the pH of the solution. And we know that that's typically what we're dealing with when we're dealing with putting an acid or a base into aqueous solution. And so in this particular reaction, I'll remind you, water here is acting both as the acid and the base, right? So our reactant side looks funny, right? Two water molecules. One of them is donating a proton to the other, and the one that is donating the proton is acting as the acid. The one that is accepting the proton is acting as the base. And so under that Bronsted-Lowry definition, we have that kind of relationship where we have both an acid and a base, and they're both water in this case. Remember, all aqueous solutions, therefore, will have some hydronium ion and some hydroxide ion in it. You don't have a beaker of water that is pure water molecules. You'll always have some of them converting into hydronium and hydroxide, and then some of them reconverting back into water, and you'll have that equilibrium in any aqueous solution that you have. What that also means is that if we add an acid or a base to water to make an aqueous solution, we're going to be affecting the concentration of those two ions. And so we need to deal with that equilibrium that is set up from the autoionization of water. And that's why we start this chapter with water itself. Okay, so if we think about this as an equilibrium reaction, we need to be able to talk about the equilibrium constant. So if we write our equilibrium constant for this reaction, we would have our concentrations of our products over reactants. So we're going to have hydroxide concentration times hydronium ion concentration divided by the water concentration squared. We don't really have a 2 written above in our equilibrium reaction, but there are two water molecules, so we would have that water concentration squared. It probably looks a little funny to you because we just spent a chapter talking about the fact that if you have liquids or solids, you don't include their concentration in the equilibrium constant because they're essentially constant. And so if we think about multiplying that water concentration squared on both sides, it's going to cancel out of the right-hand side. We're going to have it over there on the left-hand side. And we remember that that's going to be a constant. That concentration of the water itself doesn't really change because it's a pure liquid. And so instead of writing this as a Kc expression, what we do is we take this term where we have a constant times a constant, and we create a new constant. And we call that constant Kw. And we use the symbol Kw, and that Kw is going to be the hydroxide concentration times the hydronium concentration in that water. We call this the ion product constant for water, or Kw, and so it's just like other equilibrium constants, but it's specific to an aqueous solution, essentially. Because we always have this autoionization of water happening, we always have this equilibrium set up in any aqueous solution, where if we multiply the hydroxide concentration by the hydronium concentration, we're going to get whatever the ion product constant for water is. Now I'll remind you, this is an equilibrium constant. And so just like other equilibrium constants, this is dependent on the temperature that the reaction is done at. And so for our sort of typical temperature that we talk about at 25 degrees Celsius, that value is 1.0 times 10 to the negative 14th. Now notice it's only 2 sig figs, but most of the time with equilibrium constants, that's about all we have anyway. But at 25 degrees Celsius, it's 1.0 times 10 to the negative 14. This is one of those numbers you need to remember. You need to memorize it, you need to know it off the top of your head, but you also need to remember that it's only true at 25 degrees Celsius. It is a temperature-dependent constant, just like any other equilibrium constant. And so Kc, Kp that we've looked at before, remember those are dependent on temperature, so is Kw. Kw is also dependent on temperature. Okay, so let's look at that ion product constant for water. So we've got concentration of hydroxide. Remember, that is essentially the ion that we think of when we think about bases. We've got hydronium ion concentration. That is essentially the ion that we think about when we think about acids. And that multiplication will give us Kw. We will frequently write this as H plus instead of H3O plus, and I'll remind you that's really just a shorthand. H3O plus is the thing that's actually in solution. You don't have protons floating around by themselves, but for the sake of brevity and being able to write these things quickly, we do sometimes write it as just H plus. Okay, so let's think about pure water. If we have pure water, the only equilibrium constant, or the only equilibrium reaction that's happening is that autoionization of water. And so in that case, our hydroxide concentration and our hydronium ion concentration will be exactly the same. And so if we want to figure out what that is, we can just call it X. We'll call that concentration X for this given situation. We know what our equilibrium constant is at 25 degrees Celsius. And so what we know then is that we can set up this relationship. So Kw is just going to be equal to X squared because we've got hydroxide times hydronium. We know what Kw is. It's 1.0 times 10 to the negative 14th. And so if we want to know what that concentration is, it's really just a matter of taking a square root. Obviously, we're going to need the positive root here because we're using it as a concentration. And so what we know then is that X is equal to 1.0 times 10 to the negative 7th in pure water. What that tells us is if we are at 25 degrees Celsius and we have pure water with nothing else in it, our hydroxide concentration is equal to our hydronium ion concentration, and it's equal to 1.0 times 10 to the negative 7th molar. It's a pretty small number, but it's still a very important number because of that equilibrium that's set up in the water. Notice again, this is an equilibrium constant. The equilibrium constant itself has no units, but yes, the thing that we get out the end of our calculation has units of molar. And again, that's because we're not defining these things quite as precisely as we should. I'll remind you that technically speaking, these concentrations should be concentrations divided by a reference concentration. And so this is the one place where you're allowed to kind of sort of just ignore units and know that when you get to the end of it, you're going to have molar as your unit there, even though the equilibrium constant itself is a unitless number. Okay, so if we have an aqueous solution, we need to realize that even if it's not just pure water, that Kw is still going to be true even when we put other ions into the solution. So if we put acids in, we're adding hydronium ion. If we put bases into solution, we're adding hydroxide ions. And so when we do something like have a strong acid in an aqueous solution, we need to think about how does that equilibrium come into play. So let's use our classic strong acid example. If we've got hydrochloric acid in water solution, again, the hydrochloric acid, the HCl, is going to donate that proton to the water molecule, leaving us with hydronium ion and Cl- ion. Now again, effectively what that does is it adds hydronium ion to our autoionization reaction. And so if we think about that equilibrium that's already in the water, we're essentially adding a whole bunch of this product in that autoionization reaction. And we know from Le Chatelier's principle that if I add product to an equilibrium reaction, I'm going to drive that reaction back towards the reactant side. And so that's exactly what we would see happen here. We drive the reaction back to the left, and what that effectively does is it decreases the amount of hydroxide ion that's in that solution. We have plenty of hydronium ion because it's coming from the HCl itself, but any hydroxide ion that was in the solution from the fact that it's just water, a lot of that is going to disappear because we're going to drive this equilibrium back towards the left-hand side, towards the reactants. It also means that the contribution of the hydronium ion from the water goes down, but the total hydronium ion concentration is significantly higher because we've added that from the HCl itself. Okay, so let's look at what happens with a specific concentration. Let's say we have 0.2 molar hydrochloric acid. And so again, the HCl is going to fully ionize. Remember, HCl is a strong acid. If you haven't gone back and rememorized the strong acid list from first semester, you need to do that because you need to be able to recognize which acids are strong acids, which acids are weak acids. You'll need to do the same thing for the strong bases as well. So HCl is a strong acid. It's going to completely ionize into hydronium ion and chloride ion. And so what that means is from the 0.2 molar solution of HCl, we really have a 0.2 molar solution of hydronium ion. Okay, so from the autoionization of water, before we put the HCl into solution, we know we had 1.0 times 10 to the negative 7th molar, which is a pretty tiny number. And so 0.20 is a lot bigger than 1 times 10 to the negative 7th. And so because of that, if we're just concerned with what the actual hydronium ion concentration is, if we try to add those two numbers together with sig figs, it would still be 0.20, right? And we know that the hydronium ion concentration is actually even smaller than 10 to the negative 7th because we've driven the reaction back towards the left-hand side. And so with significant figures, we can really very safely approximate our hydronium ion concentration as just being 0.2 molar. So if we put that into our Kw expression, again, at 25 degrees Celsius, so we're going to have 1.0 times 10 to the negative 14th, because we're going to say we're doing this at sort of room temperature, 25 degrees Celsius. What we're going to get then is we're going to put that 0.2 molar in for the H plus concentration, rearrange for hydroxide, and what we see is, in fact, that hydroxide concentration does drop pretty dramatically. We're down to 5 times 10 to the negative 14th. I know 10 to the negative 7th sounds like a small number, but 10 to the negative 14th is an even smaller number by a pretty substantial margin. Okay, let's think about strong base then. If we put NaOH, again, remember your strong bases, NaOH is a strong base, so we're going to have an even weaker solution, 0.05 molar solution of NaOH. If we make that aqueous solution, again, the NaOH is going to completely ionize. It's a sodium group 1A metal, and so we get 100% ionization here. So what that means, again, 1-to-1 ratio, we get 0.05 molar hydroxide. And so, again, let's compare that to the autoionization of water. At maximum for autoionization of water, well, I shouldn't say at maximum. From neutral water, we would have 1.0 times 10 to the negative 7th from the autoionization of water. We've now added a whole bunch of this product, hydroxide. And so the autoionization of water, again, is going to be driven back towards the reactants. And so what we have then is we can say that we know that the 0.05 molar hydroxide that we're starting with from the NaOH is much bigger than the contribution that came from the water. And again, because it's going to decrease when we drive back towards the reactant side, we know it's even smaller than 10 to the negative 7th, and still 10 to the negative 7th plus 0.05, we're still effectively just going to have 0.05 as our concentration. So back to our Kw expression. Again, I'll remind you, this is for 25 degrees Celsius. The numbers would be different. We would have a different Kw if we were doing something at a different temperature. But at 25 degrees Celsius, Kw is 1 times 10 to the negative 14th. And so if we plug in our hydroxide concentration, we're going to end up with a hydronium concentration here of 2.0 times 10 to the negative 13th. Again, really small. So we've reduced the amount of hydronium ion that's coming from the autoionization. We still have a pretty substantial amount of hydroxide ion because we've introduced that from the sodium hydroxide itself. One small note about significant figures here. Technically speaking, we probably should only write this as 2 times 10 to the negative 13th, since in fact the concentration that we're working with here only has one significant figure in it. Kw itself has 2 sig figs in it the way that we're using it, and so we'd be limited by 2 sig figs, but we actually used a concentration with even fewer significant figures, so really our final answer is only going to have 1 significant figure in it.